So I'm offering a homework disclaimer to everybody. Somebody's been talking about what if I did the questions backwards? So yesterday's homework, probably more questions than you had to do, and maybe a little bit of busy work. And so if you want, like, be selective in those cases and do a few, and then just put them in your OneNote. So it's not going to be a big deal if, say, there were, I don't know, yesterday there were 33 questions that had a lot of algebra. Best if you do the hardest ones, just so I know you're good at them. And then, use judgment, but feel free to, not do everything if you know that you can do it. Does that make any sense? I don't know. Probably not. So we are looking at differentiation rules and some fairly simple ones today. And you've already been through the proof of the power rule. This is the generalization. The derivative of, that shouldn't be x plus h to the n. That should just be x to the n. So the derivative of x to the exponent n is just the difference quotient using h. And the expansion of x plus h to the exponent n is this great big long expression, depending on what n is. Subtract x to the n divided by h. And if you followed through, the x to the n's cancel. And then the next thing that happens is all of these h's, or a bunch of these h's, cancel. And then when we apply the limit, everything from here down is gone, and this is already gone. And so when we apply the limit, we just end up with xn times x to the exponent n minus 1. And so that is the proof of the power rule. It relies on the binomial expansion. And we are going to look at cases where n is a rational number or an integer. And believe it or not, the binomial expansion works for like fractions as well as integers. Okay, so some of this is going to be boring. If you're watching it on YouTube, you can always make it go a little bit faster. So you can use that little gear down at the right-hand side, and you can make this go faster. It makes me seem like I've got a lot of energy. Okay, so let's do the derivative of a constant. All right, so we're going to differentiate some constant c. So the constant could be 5 or 6 or 20. And we're going to do it with respect to x. And so that is equal to the limit as h goes to 0 of f at x plus h minus f at x over h. And since our function is actually c, well, that's the limit as h goes to 0 of c minus c over h. And you should be a 0. Good. Anyway, c minus c is always 0. H is some number, though impossibly small. And so that is 0. So the derivative of a constant is 0. In other words, the slope of a horizontal line is 0 everywhere. Doesn't matter what the value of x is. Okay. Derivative constant times a function. So we're going to be using some of our limit rules here. So we are going to take the derivative with respect to x of some constant c times f at x, which is just some function left undefined. So c could be 5 or 2. F at x could be x squared or sine x. So this is just equal to the limit as h goes to 0 of c times f at x plus h minus c times f at x all over h. Okay, now we can factor a c out of here, and you know what's coming next. So, so this is c times f at x plus h minus f at x all over h, and then we can use our limit of a constant times a limit is just equal to the constant times the limit. There we go. So our constant is popped outside of the limit, and this limit is just f primed at x. Okay, so there we go. Derivative of a constant times a function is equal to the constant times the derivative of the function. Okay, simple so far, right? So this is really just showing you that the derivative of some polynomial equation, for example, where the things are added together, or you've got coefficients, can be broken up into pieces. But in reality, you're not going to be like doing each individual one. You're just going to do the derivative when the time comes. Last one, derivative of the sum of two functions. Okay, so I'm going to take the derivative with respect to x of f at x plus g at x. So that is equal to the limit as h goes to 0 of f at x plus h plus g at x plus h minus f at x minus g at x. And that is all over h. Good. Okay, so we can change that to the limit as h goes to 0 of f at x plus h minus f at x plus g at x plus h minus g at x. That is still all over h. But notice I can, since this is a sum on top, I can sort of do the opposite of adding the fractions. I can break this into two fractions with the same denominator of h. And look at what's happened. The limit of a sum is the sum of the limits. And so this becomes limit as h goes to 0 of f at x plus h minus f at x all over h, plus the limit as h goes to 0 of g at x plus h minus g at x all over h, which is f primed at x plus g primed at x. Okay, so not a surprise. So if we were taking the derivative of x cubed plus x squared, the derivative would be 3x squared plus 2x. Okay, so the derivative of the sum is the sum of the derivatives. But you won't have to go through this like complicated proofy stuff. You'll just take those derivatives when the time comes. Okay, so we've looked at the power rule. I'm just going to show you a couple of power rule dirty tricks. Now you'll have to remember I said, yeah, even though we've really only shown it for the binomial expansion where n is some nice positive integer, the binomial expansion still works when n is a fraction or a negative fraction or a negative number. So we just have to take that for granted, even though we don't really know it, okay? Let's do, what is the slope of the tangent to x squared plus 3x plus 4 when x is equal to 1. All right, so we know the derivative tells us the slope of the tangent at any point that we want to put into it. And so let's take the derivative with respect to x of x squared plus 3x plus 4. And we're going to use the derivative of the sum is the sum of the derivatives rule. And so x squared becomes 2x plus 3x becomes plus 3. By the way, this is a 1. This exponent of x is a 1. And so our power rule says the 1 comes down. Our constant rule says it multiplies by 3. And then our power rule also says that this becomes exponent 0. And anything to the exponent 0 is 1. And so the derivative of this is 2x plus 3. And so the slope at x equals 1 is 2 times 1 plus 3 is 5. Okay, so that was a relatively simple one. We just used sort of the sum rule and the power rule and all those sorts of things. Okay. Not too hard to do, but maybe a little bit hard to look at. What is the slope of the tangent to y equals square root of x cubed? Okay, and let's do it when x is equal to 4. And let's hope I can do that in my head because I don't have a calculator. All right, look, aha, it's got a radical and it's got an exponent, and I don't know, oh, but I do know what to do. I'm going to write this whole thing like a single exponent just to make it a little bit easier. Okay, so this is y equals, y does not equal y. I keep asking why. Y equals x. This is going to be cubed, and then the square root. The square root is really just, let me do this in 2 steps. The square root is really the exponent 1/2. And so this is x to the exponent 3/2. Okay, now I'm going to use the y prime notation. Y primed, I'm going to put this, the exponent, out front. So 3/2. Everything is normal. Just pretend that just because it's a fraction, I'm not bothered by that. And now I'm going to subtract 1 from 3/2, which is, carry the 3. It's 1/2. Okay, there we go. So the slope of the tangent to that curve is given by 3/2 times x to the exponent 1/2. And so at x equals 4, that's equal to 3/2 times square root of 4, which is 2. So the slope is just 3. Okay. Let's do this. Let's do one that is negative. For all of those out there who might be negative. I'll just find the derivative. Of y equals 1 over 6th root of x to the 5th. All right, dirty trick. It's 1 over now. And so we need to convert this into the exponential notation. First, I'm going to convert it into the bottom into an exponent, and then I'm going to move it to the top. So reformatting it a bit, this is y equals x to the exponent 5/6, which means it's y equals x to the exponent negative 5/6, and of course x can't be equal to 0. And now I'm going to just take my derivative. I'm not going to worry about it being a negative fraction or anything. Y primed is equal to negative 5/6 x, and negative 5/6 minus 1 is negative 11/6. So I just use my power rule. And x can't be equal to 0. All right. Last thing. So try a few of these in the homework exercises. Y equals x cubed plus 2 plus the square root of x over x. And so there's a function only a mother could love. And we don't know how to deal with this function over a function thing yet, growth mindset. So we have to turn this into a form that we can cope with. So let's do this. Y equals x cubed plus 2 over x plus the square root of x over x. And so once again, we've got this, instead of adding 2 fractions that have a common denominator, I've taken this, which is the sum of 2 things with a common denominator. I've broken it apart. Now I'm getting it into a form that I can cope with. x cubed plus 2 times x to the exponent negative 1. And this is plus x to the 1/2 times x to the exponent negative 1. And I can simplify this a little bit. I'll just do that in its own step. X to the exponent negative 1/2. So y primed is 3x squared minus 2x to the exponent negative 2 minus 1/2 x to the exponent negative 3/2. Okay, so there. We've looked at all those sum rules and constant rules, and really we're just mostly, the only really new thing is this power rule, and the most complicated thing is converting everything into exponents so that we can deal with it. All right. Any questions? No questions? Good. Okay. Try the homework. It won't take very long, not like yesterday. Sorry. If you think you can do them, do the hardest ones and then move on. Okay. Good.